I believe I did find a good explanation. However, we're getting a little too close to the time where we're going to start. So if we have time at the end of the class, I can go over it very quickly. If not, you can just email me and I'll try to explain it, or we can create an office hours for later today.
Yep, that'd be great. Thank you.
Okay, so welcome everyone. So today we're going to be going over root locus and how to draw a root locus plot for various systems that we see in controls. So if you remember from your lecture, you have multiple rules that you follow to draw these root loci. And so we'll go over each and every one, and then we'll be able to essentially craft these plots, and then we can verify with MATLAB if we want later. Okay, so to get started, we have this system here with a unity feedback. And so our full equation of the system is going to be k over s plus 2 s squared plus 2s plus 5, and then plus k. And right here, as we used last week with our Routh arrays, this is our characteristic equation. And that gives us a good starting point. So from root locus, if you go back to your notes, you know that you want this characteristic equation in terms of 1 plus k, 1 plus k times your transfer function. In that case, it would be this block here. So we're going to go forward. We're going to do that, and then we're actually going to find the poles and the zeros and create our whole root locus plot. So here we have our system again. So our characteristic equation, when we rearrange it, is going to be k 1 over s plus 2 s squared plus 2s plus 5. And again, this is just our characteristic equation reorganized. And so what we see here is, if we look at the poles of this transfer function here, we have a pole at -2, 0, and then we have complex poles at -1 plus or minus 1j. So what I'm going to do starting out here is I'm actually going to mark these poles and zeros on this plot here. So we have one pole at the origin here. And then we have a pole at -1. This would be -1j. 1j. And then we have a pole at -2 here. Okay, if you're following your rules that are in the lecture notes, you know the next thing that we do is we look at and we say, okay, the loci that are on the real axis, if there's an odd number of them, so in this case we only have one showing here, we know the root loci is going to go to the left-hand side. Okay, and when we look for this one, when we're on the real axis, we can see that it's going to go to the right-hand side. And so that gives us a good indication of where the loci are going to start out and what direction they're going to go to. In terms of finding the direction out of a complex pole, we have to do a bit more work in that term. So if you look at Rule 4 of your lecture notes, we can determine what the departure angle is from a branch of a root loci for complex poles. So the way we do this is we say the angle of the pole, which is phi, is equal to the sum of the angles of the zeros minus the sum of the angles of the poles minus 180 degrees minus 360 degrees and then L. And this L can be any integer value. Essentially all it does is it puts it maps the value from 0 to 360 degrees. So if you have a negative value, just add 360 to get in a relative range. So what we're going to do in this case is we're going to have a look at this pole, and we're going to have a look at all the poles and how their angles actually affect it. So I'm going to change that, and we'll have a look at this pole right here. So this is our pole of interest. And so what we need to do is everything's in reference to the actual real axis here. And what we have to do first is we got to find out what this angle is. And then next we have to find out what this angle is. And then lastly, we need to find out what this angle is. And so that will be the sum of your angles of your poles here. And so what this allows us to do is actually determine what angle you're breaking out from these complex poles. So I'm going to go ahead and do that. Sorry, this is actually, I made a little mistake here. It's not all based off the same pole, it's based off the individual poles here. So it will look more like this. So we're finding this angle. We need to find this angle. And then we need to find this angle as well. And those will be the sum of our pole angles there. So we'll start out by going the angle of this, the departure angle is equal to 0. And then minus, in this case of this angle, this is 180 minus the tan inverse of 2 over 1. So and then we have a look at this angle here. That's pretty easy. That's a 90 degree there. And then here we have another angle, which is, we know that this is a length of 1, and this is a length of 1. So we can easily figure out what that angle is. So it should be a length of 2. So then this would also be 2 over 1, and this is negative 1 down at the bottom there. And then we have minus 180 degrees, and then minus 360 degrees times L. And right now, L, we're just going to leave as undetermined. So if we evaluate this, we actually get, in total, minus 450, and then minus 360 times L. And so as you can see here, minus 450 is greater than 360, so we want to actually map that to a value that we know. And so if we set L to equal to negative 2, we get a departure angle of of 270 degrees. Okay, so that means that this loci is going to be coming out of this pole like this.
So, quick question on L. L, do we set what L we think should be, or is L like there's a path defined?
No, so you select L. So essentially here you could have negative 450, but this is your origin. You're going to go around once, and then this is negative 450, right? So the L just allows you to subtract one rotation. So in this case, I could have left it at negative 90. If I set L equal to negative 1, it would just be negative 90. And so you'd only have to go this direction. However, I like positive angles, so I made L equal to negative 2. So that way we only have to go 270 this direction.
All right, so L is essentially just to make it so that the angle is more easier to visualize for us.
Exactly. So sometimes you might get some crazy like 1,000 degrees, right? You're not going to circle that out a bunch of times. You can just subtract multiples of 360.
Okay, thank you.
So in this question, the poles are at negative 2, 0, negative 1 with the imaginary component of 2, so plus and minus 2. So that's what you get when you just looking at this equation here. So that results in these poles here. Hopefully that answers the question in the chat. So I'm going to erase a bit of here, just to clear everything up a little bit. So now we've determined that our exit or departure from each of the poles, right? So we know the departure of the poles on the real axis as well as the poles on or the complex poles. And one thing to note, everything in root locus is mirrored over the real axis, okay? And so everything on this side must be the exact same on this side. Yes, Oki? Is there a hand raised?
Sorry, I don't fully understand the how to get the poles. Like I didn't really understand the multiples of 360 that you were talking about.
Okay, so in this case here, so when we look at the departure angle from a complex pole, we're looking at the angle from all the other poles to this pole, right? So the angle from this pole to here. And then next we go the angle from this pole to here, and the angle from this pole to here. And that becomes our sum of our pole angles here. And then essentially we get this value of 450 degrees here. And what happens is you can either take the value as 450 degrees and just know it does one full rotation, or this L factor that we see here is a scalar that you pick. It doesn't matter what the value is, but generally you pick a value so you get it within a range of negative 360 degrees to 360 degrees so that you can draw it once quickly on the plot. And so that's how we resulted in an angle of 270 degrees here. Another thing I should note, when we're looking at this, since we have 4 poles here and no zeros. N, which you're going to use multiple times in your calculation, is equal to 4, and M is equal to 0 because we have zeros in the system. I hope that answers your question. Okay, I'll take one more question and then we have to continue because there's a lot going on and I want to be able to finish a few questions in this tutorial. So go for it.
Yeah, I just have one quick question. I understand how you're doing the equation, but I don't understand where the 0 is coming from.
Okay, so this 0 here is because we have no angles from zeros. So essentially this doesn't have to be here. I just include it because this whole summation goes to 0 because we don't have any 0 angles acting on our system.
Oh, okay, I understand. Thank you.
Okay, great. Okay, so I'm just going to clean this up a bit. So we essentially have figured out what direction each loci is going, which is very helpful for the remainder of our drawing. The next thing we have to do is we actually have to figure out the asymptotes that are applied to the system. So to figure out the asymptotes, we first have the angle of the asymptotes. So this equation is equal to 180 degrees plus 360, and then Q minus 1 all over N minus M. And Q is a value that's going to range from 1 to N minus M. So in our case here, we have 4 poles and no zeros. So Q is going to equal to 1, 2, 3, and 4. And so as we can see, as a result of this, we're going to have 4 angles for our asymptotes that we're going to plot, and thus the root loci actually have to follow those asymptotes as we work through the problem. And so theta A is going to be equal to 180 degrees over 4, which is going to be 45 degrees. This is at Q is equal to 1. The angle where Q is equal to 2 is equal to 180 degrees plus 360 divided by 4. And that gets us 135 degrees, I believe. Yes, and then if we continue that again, QA with, or theta A with Q equal to 3, we get 225 degrees, and then theta A with Q equal to 4, we get 315 degrees. So what this allows us to do now is we can essentially plot these asymptotes. But all we have now is actually an angle, and we have no clue where this asymptote starts on our plane. So what we can do here is we can calculate the centroid of our asymptotes using this equation here. This again is all in your notes. So we have the sum of the poles minus the sum of the zeros of the system, all divided by N minus M. And so in this case, we have -2 plus 0 plus -1 plus j plus -1 minus j all over 4. And this results in an alpha of -1. So that means the centroid of all our asymptotes are going to pass through -1. So we can go ahead and we can now plot this on our root locus. So this is our centroid right here. And we know we have an asymptote headed out in this direction. Change colors. And then we also have one going out in this direction here. Yes, Joseph.
When we're calculating alpha, is it usual that we don't really have to consider the imaginary part because they usually always cancel each other out?
Yes, exactly, because the imaginary parts are going to cancel themselves out either way.
Okay.
Right? Yes?
Isn't the pose -1 plus 2j and negative 1 minus 2j. How come you wrote negative 1 plus j?
Yes, you're correct. That's just a mistake. Okay, so I'm going to quickly just copy this to the next slide, and then we can continue on. So, yeah, our... Okay, so now we have these directions, and we're sort of at a standstill here. And we need to know, where do these root loci actually break in, as well as where do they break out. So in order to actually calculate that, we need to take the derivative of this system. So I believe this is something that you haven't covered yet in the notes, so I'll try to clarify it as much as possible. But if we look at the characteristic equation that we had 1 plus k, 1 over s plus 2, s squared plus 2s plus 5, right? And if we rearrange this and expand and simplify, I'm just going to show our final value here. We get s to the 4 plus 4s to the 3 plus 9s squared plus 10s plus k equal to 0. We bring k to the one side and everything else to the next. We get a negative s to the 4, s to the 3. And so to find our break in and break out points, so this is where two loci will meet and they'll actually diverge in completely opposite directions. So you'll actually see that when I go ahead and plot that a little later on. The formula for that is you take the derivative of k with respect to s. And so you get a 4s to the 3 plus 12s squared plus 18s plus 10. And then you set that equal to 0. So that's what's that is going to give you is values of s is equal to negative 1, as well as s is equal to negative 1 plus or minus 1.2247j. So with this information, we can now go to our root locus plot and say, we know we have a breakout point here. So root loci are going to meet at this location, and then they're going to break away. And we also know that we have a breakout point roughly around here, where the same thing's going to happen, and where the root loci are going to meet and then break away from one another in completely opposite directions. And they actually break away at a 90 degree. And so that's actually one of the rules of root locus. So what I'm going to do here is I'm going to start drawing the root loci. So what happens is these root loci actually meet at this breakout point, and one is going to go down and one is going to go up. And same with this loci is going to come down, and see how we have three instances where the root loci meet, and every single time they're going to split at a 90 degree angle. So this root loci will come up, and then it'll follow its asymptote out. And then these lines will actually go essentially to infinity for the problem. And so now you've successfully drawn your root loci. However, you have this drawn, and it's not of much use for you because you really want to figure out what's the value of k at this location, right? Because this is going to be the k that makes your system marginally stable, right? So if you increase k past that too much, you're actually going to start getting an unstable system. So the easiest way to actually figure this out is we use our res array that we used or learned about last week. So we're going to complete this really quick. So we already have our characteristic equation here. We have 1, 9, K, 4, 10, 0, A, B, C, D. Right. So A is equal to 1 over negative 4, the determinant of this system here. And A ends up to be 6.5. B is simply going to be K. Essentially, you're dividing by 4, and then you have, or negative 4, and you have 1 times 0 minus 4 times K, so it just turns out to be K. It's super simple that way. And then our C value is going to be negative 1 divided by A, and then the determinant of 4, 10, A, and then B, which is K. And the C turns out to be 1 over 6.5, 65 minus 4K. And then D essentially will just be B, which will then be K again. So D is equal to K. So when we look at the system, we know that K has to be greater than 0 to ensure stability. And this makes sense here, right? Because the second you apply a negative gain to the system, the root loci is actually going to go in the opposite direction. So this is what happens when you have a negative gain. So what this shows you is that essentially this Rouse array shows you that we have to have a positive gain for this system to be stable. Okay, and then if we look at our C parameter, we know that C has to be greater than 0. So essentially this 65 minus 4K has to be greater than 0. And if you bring it all to the other side, 65 divided by 4 has to be greater than 0. That's right. Sorry, like this. That means K has to be less than 65 divided by 4, which is 16.25. So in this case, we're stable in a range between 0 and 16.25. And then at 0 and 16.25, we're marginally stable, and where we're always going to have either some oscillations or some error. So this K value here is going to be equal to 16.25. And so what this shows you is once you increase your K value past this, you're going to have significant oscillations, and when you're at your marginally stable portion, and then once you increase K past 16.25, you're actually going to become unstable, and your response would look like this, and so on and so forth, and then it would essentially go to infinity, and then yes, thus your system's unstable. So let's say you want to see what frequency you're actually, what frequency occurs, or what frequency of oscillation you're going to get at this point. The easiest way to do this is we can now take our characteristic equation here and plug in K is equal to 16.25, and then plug in S is equal to J omega into the system. And since we know the real part is equal to 0 because we're on the imaginary axis, we can actually figure out what the frequency is at that point. So we're going to go ahead and do that now. So again, we're replacing S with J omega. And so with S to the 4, we get omega to the power of 4 minus 4J omega to the 3 minus 9 omega squared plus 10 J omega plus 16.25 equals to 0. So what I've done here is j squared is equal to -1. And so that's why this one is equal to positive, because a negative times a negative, again, is a positive. So we're going to go ahead and we're going to split this into its real and imaginary parts. So we have the omega to the 4 minus 9 omega squared plus 16.25. And then we're going to do a plus j, and then 10 omega minus 4 omega cubed equals to 0. And since we're on the real axis, we know that this whole system is equal to 0. And so all we have to do is we set the remainder of this equation now to 0. So at this instance, omega is equal to 0, or omega is equal to, in this case, the square root of negative 10 over negative 4, which is equal to plus or minus 1.5811j. So the actual location of this pole here is at 1.5811j, which means if you set a k value to 16.25, you're going to be marginally stable, and you're going to have frequency oscillations that are at 1.5811 radians per second. Okay, so you're going to essentially, this way that you get at your marginally stable system is going to have this frequency here. Is there any questions about this question before I go on to the next one? Any clarification I can bring, please let me know. Yes, Aiden?
Back when we were grabbing the original angle of 270, were we doing that from a specific point or just the angle of all of them?
Here, right?
Yeah, because you originally said a specific point, and then you said no. I'm just trying to clarify that.
Yeah, sorry. So I messed up initially. So how it works is you look at each individual pole here, and everything's in reference to the positive real axis. And so if you want to find the angle of departure of this pole, you have to look at all the other poles and zeros that are on your root locus and find the angle from their positive real axis to the root loci here. So in this case, we have this angle here, which is this system here, this negative 90 from this pole down here, and then, sorry, I apologize, my tablet's doing some weird things today. And then from here, we also have this angle, which turns to here. So it's the angle between the real axis of the pole you're looking at to the desired pole that you're looking for the departure angle. I hope that clarifies things a little better.
I think so, because I was just a bit confused of what the actual angle was doing specifically when the rest of it seemed like we didn't need it.
Yeah, so all this angle gives you is the departure of your pole, right? So we'll see in a couple more examples. We'll see how many we get through today. But it significantly changes based on the amount of poles and zeros that you have in your system. And so this could come out at a 45, and then your root locus looks completely different based on the amount of poles and zeros. So maybe we'll do one more question, and then that will clear it up a little bit more.
Yep, okay.
Okay, so second we have a...
Hi, sorry. Could you just go back one slide for 1 second? I just want to make sure I got the right thing. Okay, thank you.
Also, it's important to mention that this omega equals to 0 is because of this pole here that's on the imaginary axis. Okay, so now we're going to look at just another system here, just to get yourself comfortable with actually drawing root loci. And so what we can see here is our k values actually in the denominator of the system. So we're actually going to have to do a bit of rearranging to get that normal form that we're used to seeing with root locus. So again, the form that we want to see is 1 plus KHS, where this is your transfer function here. And so currently, we have S, or 1 plus S divided by S squared plus 1, S plus K. And then we can multiply this up by the 1, or multiply the top and the bottom. So we have S squared plus 1, S plus K, and then plus S. This whole system equals 0. And now we can go ahead and we can bring all these values out. So we have S cubed plus KS squared plus S plus K plus S equals to 0. And now we're going to group everything. So we have an S, S squared plus 2, and then plus K S squared plus 1. And again, in order to get our standardized form, we're going to divide the whole system by S squared plus 2. And so we get 1 plus K S squared plus 2 over S squared plus 1, and then this one's S squared plus 2. Okay, so this is our standard form that we want to see for root locus, and this is our characteristic equation. So what we're going to go ahead and do now is we can see that we have now 2 poles and 3 zeros. So n is equal to 3, n is equal to 2, and our zeros are at our zeros are at 0 plus or minus. So m is the number of zeros in the characteristic equation here, and then n is the number of poles. So with the zeros, we have plus or minus 1j, and then the poles, we have 0, and then plus or minus 1.4142j. Okay, so first thing we're going to do is we're going to have a look and plot these poles and zeros on our axes here. So we have a 0 at 1, and then a pole a little higher than that, and a 0 and a pole, and then we have a pole at the origin here. So as I mentioned before, we're going to first look at all the poles and zeros on the real axis. And so what we see here is we have an odd number of poles and zeros when we look at this pole here. So we know that this loci is going to go all the way to infinity in the negative direction. Okay, and that's just one of the rules of root loci. So similar to what we've done before, we're going to actually find these angle of departures as well as the angle of arrivals of the poles and zeros. So for simplicity, I'm going to look at the
Sorry, could you repeat that rule again? So you said something about having odd number of poles or something.
Yes, so when you're looking at loci that are on the real axis, if there's an odd number of poles and zeros at this location, at the location that you're looking at, the root loci goes to the left. But if there's an even number, it goes to the right. So if we go back to the system we just looked at, here we have an odd number, so it's going to go to the left. Here we have an even number, right? Because if we look on the location of the pole as well as everything on the right-hand side, we have 4 poles. And so it's even, and then the loci is now going to go to the right-hand side. Okay, so now we're going to go. Yeah.
M we get from the numerator and N we get from the denominator pretty much?
Yes.
Cool.
Yeah, it's actually the order of the numerator and the order of the denominator. Okay, so quickly we're going to look at the angle of departure and arrival. So we're going to look at this pole up here. And so first thing we're going to do is actually write out our equation. So the sum of the zero angles minus the sum of the pole angles minus 180 minus 360 degrees, and then L. And so we'll have a quick look here. And we're going to start with this pole, this zero, this pole, and this zero. So what you see here is every angle here is actually 90 degrees. And so this makes everything very simple because we don't actually have to do any trigonometry. And so we have the sum of the zeros, which is going to be 90 degrees plus 90 degrees. And then we're going to minus the poles, which again are going to be 90 degrees, and then 90 degrees. Then we have a minus 180 degrees. And then so the result of this is actually just negative 180 degrees. So we know that this pole is going to have a loci that looks out in this direction or departs in this direction. We can look at the same thing in terms of zeros to figure out what their angle of arrival is. So it's a very similar method to what we have done before. Yes?
Sorry, I know you said something about the L. So what happens to the 360? Did you like choose 0 or something?
Yeah, I chose L is equal to 0. Right, so I'll say 0 times 360. Yes.
For the pole in the middle, we just count that as 0 degrees.
No, we count it as 90, right? So we have one here, which is 90.
Yep.
Here, I'll outline them in a different color. So we have this as our 90 here. We have this one as this 90. And then we have this one as this 90. And this one as this 90.
Oh, because we're starting at P1. Okay. That makes sense.
So to answer the question that's in the chat, the purpose of L is just essentially to map the angle between negative 360 and 360, because you potentially could have this value as like, I don't know, 1200 instead of something in the range of negative 360 to 360. So essentially all you're doing is taking away factors of 360 until you get a value that you can plot and easily plot on the root loci. Okay, so now we're going to do the angle of arrival for this zero here. So we'll call it Z1. So this now is going to be the sum of the pole angles minus the sum of the zero angles, minus 180 degrees, again, minus the 360 degrees times L. And so what we're going to do here is you have to look at all our poles. So we got this one, this zero, this one here, that one there, and that one there. And so we're going to actually do a top-down approach here. So as I talk through it, so with this pole here, we're going to have a negative 270 degrees, right? And then we're going to add 90 from this pole here. And we're going to add another 90 from this pole here. And then we're going to subtract a 90 from this pole here. All right, and then that'll get us 360 degrees times L.
Sorry,
I forgot.
the 180 go?
That's exactly the mistake I just found in my calculator. So thank you for pointing that out.
No worries.
right? So, and then minus 180. And then, so this turns out when L is equal to 0 again, this turns out to be 180 as well. So we know that the pole is going, or the loci is going to arrive at this angle here. And as I mentioned before, everything is mirrored over the real axis now. So we can actually go forward and plot the rest of our root loci here. We should actually go and do our asymptotes first. However, what you'll see is that actually doesn't matter in this regard, because we already know what this root loci will look like. So it's going to exit this pole and then come in like this, and the same as this system here. And then we know that this loci is also going out to negative infinity. So does anybody have a guess of what's the range of stability for K in this question?
Smaller than 0?
So 0 to what?
Infinity.
Yes, exactly. So essentially at 0 and infinity, we're marginally stable.
Is that just because of the fact that we have both the 0 and the pole at the imaginary?
Yes, exactly. So what happens is when K is equal to infinity, you're at your 0, right? And when K is equal to 0, you're at your pole. And since they're both on the imaginary axis, when you reach infinity or 0, you're going to have a marginally stable system.
And then anywhere in between that, you would be a stable system.
Exactly. And so that's why root locus is very helpful, and it's a good visualization. I know it's sometimes frustrating or hard to learn how to draw it, but just if you plot the root locus of a system, you can easily see that, okay, this is stable for essentially all positive gains. Yes, there's one last question.
Yeah. So is it 0 and infinity? This system is marginally stable, or is it between 0 and infinity?
No, so at 0 and infinity, it's marginally stable, meaning you're going to have constant oscillations, right? But anything between 0 and infinity, so if we did the Routh table for this, you'd get a value like this, right? Which is essentially, you'd only really detect this. And so that means if K is equal to 0, it's going to be marginally stable, meaning you're going to have constant oscillations. However, when you reach infinity of K, which you can never ever reach, you would technically also be marginally stable.
So if K is in between 0 and infinity, is the system underdamped because those poles, those little half circles, are more dominant than that pole on that line, real axis?
Yeah, so that actually depends on the actual scale of the root locus here, right? So I don't have any scale in this direction here, but if we'd like, I think we're running out of time to do the last example. But what I can do is I'll pull up MATLAB, and then we can just quickly plot the system, and then that way everybody can sort of see what it would look like, and then essentially you can make your assumptions based off that, if we'd like to do that.
We're not gonna get any frequency from this one, right?
Yes, you would always get frequency.
So you're not solving that.
So you would always have frequency, but instead of being marginally stable where the frequency is there forever, let's say if your gain gets you to this location, your response is going to look like this, and you're going to diminish down to essentially 0 frequency at some point in time, right? However, if your gain is set to 0, you're going to be marginally stable, and you're going to have a frequency response like this forever, regardless of your input to the system. And so based on that, I was going to go over the last example, but there have been a lot of questions. So, and we only have, yes?
Do you mind posting these solutions after, if that's okay with you?
Yes, I'll post. I have a clean version of the solution, so I'll post that instead. But then, yeah, so you can always have a look at it. Okay, so I'm going to. Okay, so we're gonna, everybody can see the screen. I'm sorry the text is a little small. I'm going to scale it up when I actually plot the locus itself. However, if you're curious, the command's just R locus, and you put a transfer function in the middle, or not in the middle, you give it a transfer function. You do.
Can you zoom in a bit? It's a bit blurry. I'm not sure.
Yes, I'm just, I was just gonna plot it for you.
Sir, you stopped presenting.
Yeah, sorry, I just ran into one issue there. So hopefully you can see this now and it's pretty clear, right?
Yeah, it's clear.
Okay, so essentially this is the root locus that you're going to see here. And so I forget who asked before, but if this was always going to be underdamped. So what you can see here is at -1, we're at approximately 0.2 or -0.2. So you're going to essentially, yes, always be underdamped in this situation. However, it is stable for all ranges of K. And so that's the solution to that. And then if you have any questions, please feel free. You can shoot me an email. I'll try to post the solutions to this shortly. However, yes, that's all that we have for today. So thank you, and then we'll see you next week.
Have a good day, sir.
Sorry, I just wanted to ask if anything, because I know there'll be some questions about like the stability and all, but like, do we have to like for the